Cool. All right. Hi everyone. When we dive in, cool. So before we get started, just a couple quick intros. My name is Allain. I am an Eng lead at Dropbox. You may also possibly know me through CppCon, which is a website that I've run since 1998, or maybe my book Jumping into C++, which is targeted at beginners who have perhaps never programmed before, helping them to learn both to program and to write good C++. I also want to introduce my co-presenter, Andrew Twyman, who's sitting up front. You'll see a lot more of him later. He's a tech lead on the team. And Jacob Potter, who has written a tremendous amount of code and responsible for a large portion of our open source contributions. He won't be speaking, but feel free to ask him questions. Cool. So we all work on Dropbox's internal platforms and libraries team. Basically, our goal is to make cross-platform development easy, basically feel like it's zero cost compared to writing natively for a particular platform. So before we dive in, let's get to know you guys a little bit better. So who here has written any code for Android in the past? Cool. iOS? Awesome. Any other mobile platforms from folks? Excellent. BlackBerry, I hope. Or perhaps WebOS, something like that. And how many of you have gone to any of the other talks, either from Dropbox? Oh, excellent. Well, welcome back. Or the Microsoft talks on similar subject. Cool, sweet. So this talk will not cover the same material. There will be a little bit of overlap, of course, but our goal is to sort of actually arm you to make your own new mobile apps. So our structure will be basically, you want to make an app, here are the principles that we followed, and hopefully give you a framework for thinking through the same process. We'll talk about the challenges we faced and some of the tools that we have created to make this easier. Well, one particular tool that we'll also be discussing later. So the first question that you probably want to answer is, do you want to make an app? I'm assuming the answer is probably yes. In that case, you need to decide, does it need to be cross-platform? And hopefully this graph will give a little bit of insight into that, so you can see that, and oops, that's the wrong button.
Just hit play.
Play? There we go. All right, laser pointers, not for the faint of heart. You can see the top there, that Android is clearly winning in terms of market share, that's sales month by month. But what's really important is the bottom graph here, where you can see that while Android has a sizable lead, it's not like iOS is going anywhere. So both are still super important. So we would say the answer to should it be cross-platform is probably yes. There are some circumstances, maybe you're a one-person startup. Anybody here a one-person startup? Cool, don't have to address that. You guys probably shouldn't build for one platform then. If you were, maybe you should consider that. So our answer to this is support both. So the next thing you want to decide is what is your overall approach to this problem. So one approach you could take is to build everything native. So you could write one app in Java, one app in Objective-C, and okay, there you go. So Dropbox did this. This was the first Dropbox app, the one you're probably most familiar with. We call it the core app. It gives you a file system view on your phone. You can browse your files, you can open them, preview them, things like that. So there are obviously a few problems with this approach, and we ran into a bunch of them. So one problem, of course, is you have two separate code bases. And that means you've done a lot of work twice. In particular, that means you're going to have a lot of the same bugs. You're going to take a lot of conceptual overhead as well. So for example, if you build a new feature, you might have one person who goes in and decides, I'm going to add support for file previews into both of these two apps. That's great. Now they get to learn two separate code bases that were written by different people, so they probably have totally different concepts. They're going to look different. And so you're going to learn not just the languages, two different languages, but you're going to actually learn two different sort of entire application stacks. And you can fix some of that with communication, but you still have a lot of overhead at that point. You have people having to talk about, well, I'm going to design my thing in this way, my thing in this way, and there's two different platforms that have very different constraints in the first place. So that's a bunch of downsides. Concrete example here, a lot of you probably heard this, we ship camera uploads for both iOS and Android. We ship them 4 months apart. because it just took a long time to build things twice. Your other approach, which is in a lot of ways a lot more convenient as a developer, is to build it entirely custom. So this is much more similar to the Dropbox desktop client, where we wrote it all in Python. No booze, please. It works pretty well on desktop, Windows, Mac, and Linux. And that means you implement things once, obviously, and that's great. Now there's a downside. So this screenshot here is actually a rendering of the Dropbox desktop notifications, notifications in sort of recently changed files. We wrote this in WebKit, actually. So it was great. It worked across all 3 platforms, no trouble. So we wrote it once, except that when we shipped it, we had a huge outcry from all of our users because it didn't look native. And they got really annoyed, especially the folks on OS X, actually. They're really picky about things fitting in. And so we actually had to go and talk about writing things once. We got to write it once one more time to make it look native. So we did ship that, but we ended up kind of spending a lot more time on design than we'd intended to. So there are definitely some pretty serious downsides to building everything custom. And the major downside, of course, is your users, they're not switching between their 2 phones, hoping that Dropbox looks the same. They're switching between apps on their computer. And that leads us to the third option, which we also did learn from our mistakes or from our past. This is the native UI with a cross-platform core. So this is a screenshot of the Carousel photo gallery app. And we wrote all of the UI here that you see. This is written in Java, Android, standard Android. And then all of the underlying data layer is written in C++, and that's what we're going to talk about. You can see the animation. It's quite fast and native. And nice thing, no gray squares. Cool. You've probably all seen this in the previous talk. So everything else in this talk is going to follow from this particular design and its consequences. If you disagree with this approach, this probably won't be super interesting. Cool. So you want to write a native UI, but you don't actually want to write everything twice. What's the consequence of that? It's basically this architecture. So you have 3 layers at heart. You have a cross-platform business logic layer written in C++. It's probably what you're all super familiar with. We're writing some C++ code to do something. You have a language bridge. So this is either JNI on Android or Objective-C++ on iOS. You could also go with the C wrapper route, but that's not what we propose. And then you have the UI that's platform specific, written in either Java or Objective-C. The core thing that we found is that the UI layer is kind of the prime mover of the app. Main lives here, calls through the language bridge, talks to the business logic to make things happen. Just to expand that out a little bit, what does the rest of this look like? So if you're going to write an app, some things you probably need to be thinking about. This isn't an exhaustive list, but hopefully it gives you a little bit of a structure for, these are things I should pay attention to. The things that are in bold are things that we'll do deep dives into later, either me or Andrew. The other things that I want to talk about, I'll just touch on briefly here. The UI view layer, that's obvious. The view model layer is actually really interesting. So we have basically a view model architecture. And what we found is that pushing the view model into C++ can work really well as well. So you end up with a view layer that's kind of the thin platform layer. The view model itself, even though it does now have some platform idiosyncrasies in it, the bulk of that logic is still the same, and that's a lot better for you. And then you have your business logic library, what we talked about. In terms of libraries, we don't have much to say about storage, caching. SQLite's fine. Curious what you guys are using, potentially come up and tell us afterwards. Probably have something to learn there. Use any third-party libraries that work across all of the platforms you need to support. That is a little bit of a catch. And then, a note about the build system, since you're probably going to want Xcode files and Android make files, and potentially if you go to desktop, things like Visual Studio Solutions, maintaining 3 build systems in parallel kind of sucks. We have found good experience with GIP, generate your project, from the Chromium folks. C makes another alternative, but just be aware that you will want to think about that early. Cool. So one thing that I didn't touch on too deeply in that last slide is the specialized platform features. So what are these? These are things like GPS, or maybe on iOS, and then like background fetch, wake locks on Android, things like that, where you can't get to them any other way but through the platform. And so that actually leads to a small change to our overall architecture. So we have both the UI, which is platform specific at that layer, but also the platform services layer. And so the actual control flow will often look sort of like a U shape. UI called into the language bridge to the business logic. Potentially that business logic layer now needs access to something in the platform services layer called back out through the language bridge. And we do this essentially by passing in a vtable that allows us each layer, each platform to provide a set of callbacks that the business logic can use to access the platform services. Cool. So let's talk a little bit just about a couple of these layers. First is your UI layer. And so what are some good principles that you should try to adhere to here? So first of all, keep your UI layer thin. This is the code that you're going to write n times, probably starting at 2, maybe more. So it's not great if you have a lot of logic here. On the other hand, you should that's not UI logic. On the other hand, you should follow the native UI conventions and patterns. That means both look and feel, so make it look like the native app, but also just go with the platform's idiomatic code. This is probably somebody in your organization who knows Objective-C really well. That's great. They should just go to town on that. They shouldn't feel the need to, totally adhere to, your C++ standards and things like that. This is where you want it to be idiomatic. And there's just not going to be that much code in this layer. So as a result, it's not such a bad thing. You don't want to optimize for it being, necessarily uniform if it's violating platform conventions, because people are going to be thinking about it in the platform here. And as I mentioned, one reason you can keep it pretty thin is the view model in C++. Another layer I want to talk about is the language bridge itself. So hopefully there's not any big surprises here, but again, you really want to keep this guy super thin. The code is really ugly. It's hard to get right. JNI is pretty gross. If you're just like hand coding it, it's not fun. It's a little bit like programming in assembly instead of in typed language. And it's very boilerplate heavy. So you really want to avoid things like putting real logic in there. 2 reasons. One, it's just going to hide that logic. You have a bug. People are going to be like, well, probably not coming from that layer. It's just passing parameters around. And the other part of that is if you start, if you're not careful, that layer becomes sort of this new API that's tuned to each platform. So instead of having a very clean C++ API that all platforms are coding against directly, you now have, well, on iOS I'll do this one little thing here, and on Android I'll do this one little thing there, and soon enough you have 2 different implementations that have all been written in some of the worst possible place to put it. And another thing, and so that goes to have consistent interfaces and be careful, things like types that are not available in one of your apps. So if you, or one of your platforms, I should say. So if you end up using unsigned, maybe somebody writes their iOS feature and they're like, yeah, I want an unsigned integer. And now somebody who's working on the Java side is like, oh, that's not so good. And then they go and they have to go change all the code that depends on that on the Objective-C side, and now they have to go recompile an app when they've maybe not even set up to do it. It's super annoying. So you want to keep it common. It's not too surprising, but will save you a lot of pain touching a lot of layers that people aren't used to. And ideally, you can auto-generate this code. And in fact, Andrew will be talking a little bit later on about a tool we have that can help you with that. So at this point, I'd like to hand it off to Andrew.
All right, am I live? Can you hear me? Good. All right, so hi again, I'm Andrew. I've been working on our cross-platform C++ code base pretty much since its inception, when it was just a small library we were using for one of our SDKs. Now it's something that we're actually building several different applications on. So I want to share some of the things that we've learned along the way, problems we've had to solve so that you guys don't have to solve them again, and do a bit of a deep dive into more of those items that Alex alluded to. I'll start with how we deal with the language and the standard library across platforms, dive into some of those platform services that Alex mentioned and where we found that architecture to be particularly useful. I'm going to dive a little bit deeper into the language bridge and show you what that looks like if you have to write it yourself and what the issues are. And then I'm going to show you how you can just not write it at all by using a tool that we're going to share with you today. So let's go ahead and dive in. First, a reminder of what our situation is, and your choices about how you approach these things might be slightly different if your situation is different. We like to move fast. We're still a pretty small company. We still try and act like a startup, even though maybe we're a little bit beyond the size where we can call ourselves that anymore. But we need to sweat the details. We're storing users' data. We can't afford to just move so fast that things break and we lose the users' data or corrupt it because they have to trust Dropbox. We're building mostly new apps. That means that we're not dealing with huge legacy code bases that was built for old platforms. So for the most part, we can do things right from the beginning and avoid some of the pitfalls there. Someday we're going to have the legacy problem, and I'm hoping that we build things well enough that it will be surmountable. But for now, this architecture is not optimized for dealing with that. And lastly, we're building multiple apps. So we don't only care about being cross-platform in a single app. We care about reusable libraries that can be used across multiple apps and giving those apps a consistent architecture so they can easily reuse common features. So given that as context, we want to use C++. It's pretty much the best thing that's available across platforms that you can build everywhere. But unfortunately, platform support for C++ is a little bit uneven on the platforms that we're working with. The compilers have different levels of support for C++ 11 and 14 features. They have different STL implementations with different bugs. And one particularly tricky one, we like to keep our warnings turned up pretty high to catch bugs early. All of the compilers have slightly different behavior there, even if you try to turn on all warnings. Yes? I will in a couple slides, yeah. So we've found frequently that something that compiles just fine with one compiler will trigger a warning on another compiler. Usually that's not noticed until the automated build builds all platforms because most developers will be focusing on one. Little problems like that we'll then try and tweak the compiler settings to avoid it again if we can. So based on this, our approach is to embrace the new as much as we can, use the newest tools that we can get on any given platform, though only the ones that are stable enough to use in production code. And we'll use any language features that we can as long as all the compilers on the platforms we care about support that language feature. We unfortunately can't really build language features ourselves. We're not quite to the scale where we can build our own compiler. But what we can do is we can try and raise the level of the libraries. So if there's anything missing on individual platforms that we really want to use, we can fill those gaps and try and give the application developers a consistent environment to work in. And we can write for portability from the beginning and then refactor when we find out that we did something wrong. Our code base isn't yet too big to do that, and maybe if we can borrow some of the tools that Google was talking about, it'll never be too big to do that. So examples of that would be using fixed width integer types, at least when transferring data between languages across the interface, saves you from the problems of 64-bit versus 32-bit. Java doesn't allow use of unsigned integer types, which is another thing we can just avoid, at least in that boundary. And we can use UTF-8 to represent our strings everywhere, so we get a consistent experience in our code everywhere. And now getting to your question of exactly what we use. On iOS and also OS X, we use Clang and LLVM, version 3.5 right now. This is the one that comes with Xcode 5. We'll be switching to Xcode 6 very shortly, now that the GM release of that came out yesterday or 2 days ago, something like that. On Android, we use GCC. We've taken a look at Clang on Android a couple times, but run into problems. It's probably time to take another look, so we may be able to unify that and save some problems. But on the other hand, having 2 different compilers on production platforms also keeps us honest in terms of portability. We also build our code on OS X and Linux using either of those compilers, both for unit testing and for a set of wrappers for calling it from Python. That's not something we've released, but it is something we use for internal prototyping and testing. It's quite useful. And lastly, Windows is something we're working on. We're looking at Visual Studio 2013 and the 14 preview, which is apparently not actually going to release in 2014. The good news is 14 actually supports pretty much all of the language features that we need for the code that we're writing. 2013 doesn't quite yet. The bad news is that 14 is still in preview and we're not allowed to ship code with it. So we're still working on this, and we'll see what happens over the next couple of months. So given that language baseline, as I said, we can try and raise the level of the libraries to where we want them, even if some things are missing. For instance, we make a lot of use of optional, which I'm sad to hear didn't make it into C++14, but we like it. So we've pulled in an open source implementation that we can use consistently across platforms. Make unique wasn't in C++11, so we just wrote our own because we like that model. Thread locals are not available on iOS and actually broken on Android, if I recall correctly. So we've made our own replacement for that for the few cases where we need something like that. We can't use toString on Android because it's disabled with an ifdef in the library because of some problem or other. I don't actually know what it is. So we wrote our own. From string doesn't exist, but normally you would use iString for converting things from strings. We found that hangs if you try and use it on Android for certain types, so we just wrote our own instead. And then, of course, we're building our own libraries just as general useful things. This is probably the kind of thing you've built all over the place. You know, we have a little run on exit helper. This is like a scoped guard for easy cleanup of resources that aren't spark pointers. You know, we have string formatting, all the kinds of things that any good C++ code base wants. We try and build those as we need them. Not as deeply as we should. We're getting to the point where we really do want to start looking at things like that. And we started to look at Boost and also at borrowing code from Chromium as good cross-platform libraries. But I'm not educated enough on that to say what the right answer is yet. OK, so that's enough said on language and libraries. Now I want to dive into some of those platform services where we're actually leveraging the platform from C++. So let's start with networking. As you'd imagine, we are Dropbox. We are a cloud services, cloud storage app. We care about using the network. But at what layer should we handle this? There are two options. You can either use the platform frameworks, which are pretty strong. By platform frameworks, I mean, you know, Apple's frameworks or the Java runtime libraries. Or we could use a set of portable C++ libraries that do networking in a consistent way. We actually have different apps that have made different choices here, and I'm going to give you an idea of both and why. So choice number one, do it all in C++. That's probably what you're used to as C++ developers. There are a lot of good portable libraries for doing networking out there. Benefits are you get a consistent set of features and bugs regardless of what platform you're on, usually. Occasionally there are platform-specific bugs. And you tend to get pretty good performance because you don't have to go through that language bridge. There's no marshalling. You've got direct access to the hardware and the benefits of C++. But it's up to you to get the details right and to bring together all the right pieces. The libraries here tend to be piece by piece. You know, you need OpenSSL, you need WebSockets, and you put those together into whatever you need rather than getting one nice high-level thing that does everything you want. This is the approach that the Mailbox app is used for its email backend. Notably, they're not using HTTP. They're using a direct WebSockets-based protocol. So they don't benefit from a lot of the features that the platforms build on top of the raw networking. So they found that it was a benefit to go this way. The alternative is to use the platform frameworks that are provided. Mobile platforms in particular have pretty strong libraries for doing this kind of thing because most mobile apps want that. The benefits are you get feature and security parity with other apps on the platform. This was a particular benefit we wanted when we built our SDKs. They run inside of other apps, and it would be best if we didn't introduce new and different security bugs than the apps are expecting on that particular platform. But if our security bugs are the ones that Android has, then the app expects that, and they know how to deal with it. Or if they don't know how to deal with it, at least it's not our fault. What? Yeah, precisely. The other benefit of this is we get lots of features for free. Connection reuse, proxy configuration, all the stuff that goes with HTTP. We don't have to think about it because, for the most part, Apple and Google have already thought about it. Another advantage is we don't have to push updates because that's not our job. The disadvantage is we're subject to the vagaries of the platform. If there are any limitations we don't like about the platform frameworks, we have to work around them. And if the only time we get updates is when the platform itself gives an update. And if you've worked on Android, you probably know that not everyone upgrades immediately because they can't, because their cell phone service provider doesn't let them. So you've got to deal with old versions. This is the approach that we've used for most of our interaction with the Dropbox APIs, which are what's behind all of our mobile apps, with the exception of the email backend for Mailbox, which is specialized. But we've made a couple hybridizations of this approach. For instance, Carousel does use the platform frameworks, but they also ship their own jar on Android to replace the HTTP library at the Java level with a specific version, so at least that they don't have to deal with the different versions on every Android platform, but they're still using the Java runtime and that level of features. So given that we want to do that, how do we expose this so that C++ can actually use it? The C++ code just sees a class called HTTP requester that we've built. It's specialized to the Dropbox API. It's not a generic HTTP thing. It knows how to do things like authenticate to the Dropbox server, encode parameters, and decode JSON in the response, dealing with our REST API. It has a synchronous interface, meaning you ask for a response from the network and then this thread waits for it. That's okay for us because it's only ever used on background threads that are doing the background syncing. The way that HTTP requester does the raw HTTP calls once it's decided exactly what should go over the wire is it uses an abstract interface. It doesn't know where that implementation is. And it's the platform layer or the app layer that is specific to a platform that's providing the implementation of that interface. So in Java, that's based on HTTPS URL connection, though with a bunch of glue code in between. In Objective-C, that's NS-URL connection or NS-URL session, which can do background fetch. And the adapter code that glues these things together and provides that abstract interface is responsible for translating any differences in the features. So for instance, the NS-URL connection model is purely asynchronous. We turn it into a synchronous interface for exposure to C++ so that we get the same thing across Java and Objective-C. So moving on from networking, I'm going to talk about how we do background threads on various platforms. This is a tricky bit that we were lucky enough to be conservative about from the beginning. We've learned a few more things about that, but mostly what we did turned out to be correct. So your library wants to manage background threads. We want the C++ code to be in charge of that because it's part of the app logic to decide how many threads I need and what they should do and how to coordinate them. However, some of the frameworks that we plug into don't really like threads that they didn't create calling into them. On Java, you can theoretically attach JNI to a thread that you created, but we've seen issues with the class loaders, that if you try and access a class that hadn't been loaded yet, it won't actually work properly. Python, in a similar situation, if you call into Python on a thread that it didn't create, it doesn't have a thread local, or it gets a new version of a thread local every time you enter Python, which is not usually what thread locals are supposed to mean. It turns out Objective-C actually doesn't have any serious issues here, other than the general issue that you get slightly inconsistent debugging information depending on how you created the thread, how its name was assigned, things like that. So the way we solve these issues is to also expose threads as a platform service. So the platform provides an interface through which the C++ code can create a thread. It provides a name and a priority, and then a lambda, which will be called on the thread when it's created. That lambda can also capture any resources needed through a shared pointer so as to make sure that things don't get deleted before the thread can even get around to using them. And then once the thread is created, C++ owns it, and everything is normal C++ concurrency code that you're probably familiar with. And C++ will tell the thread to shut down when it needs to. There's no special mechanism in Java or Objective-C that has to deal with this. And this has saved us from all those headaches that I mentioned of thread locals being wrong. Is that question?
Did you consider doing, instead of having threads, having like dispatch methods and then let the operating system do their pooling and all that stuff?
Absolutely. One of the areas that I'm going to mention in future work at the very end is asynchronous frameworks. We're using a pretty low-level concurrency with threads and mutexes, and that's quite complicated, particularly for application developers who might be used to a higher level or like asynchronous event model. We've built a few layers on top of that of our own, but we're actually looking to find something good that we can adopt without having to build it all ourselves. That's another kind of open area. Yeah, through the C++11 exposure of it, but pthreads is what's underneath that, at least on the platforms we're talking about today. Okay, now I'm going to move on from specific features to how we bridge the languages so that all these things that I mentioned to you can work. And I'm going to do those starting with Java and then moving to Objective-C. Starting with Java, I want to poll the audience again with a slightly different question, because nothing that we do with Java is specific to Android. It's just specific to Java. how many people have done programming in Java at all, any platform? Cool. How many of you have used the Java native interface to hook it up to C++? Quite a few, okay. How many of you liked using the Java native interface? No hands. That's pretty much what I expected. Okay. So many of you know, but some of you don't know, Djinni is the Java native interface. It lets you link Java to native code, and unfortunately there are two definitions of native here. For Djinni, native means not Java. For us, when we're talking about platform-specific code, native means Java. And it was designed really for isolated calls across the boundary. You wanted to call into C++ to do some big, complex calculation that was CPU intensive, get back a result. Or you wanted to have a specialized driver for your specialized hardware, you could do that using Djinni. In particular, those things are all cases where you wouldn't cross the boundary very often, and what you're passing across the boundary frequently is very low-level primitive types. At least, I think that's what Djinni is good for, or most useful for. They do, and I'm very sorry for whoever has to write that. Yeah, I mean, Djinni can work for everything, and I'm going to show you how, but places where it's easy is where you're doing simple things like this. And the NDK documentation for Android actually has a whole paragraph telling you why you shouldn't use the NDK and you shouldn't write C++ code. But we ignore that because we're special. So Djinni gets ugly. There's an impedance mismatch, different memory models. So you got to do marshalling of data. There's a lot of manual steps to go through in order to make everything work. Most of the resource management is very manual. This is really a C interface with the only part of C++ is, yeah, there's a big object that all of the C functions are in as member functions rather than as function pointers. And most importantly, at least to me, is there's no type safety here, which I find astounding because we're linking together two of the strongest compile time, statically typed languages, being Java and C++. But what's between them is a boundary that is entirely dynamic and generally crashes if you get something wrong. So the way Java calls to C++ usually is it just looks up a symbol, if you was using a magic name, and then it'll call that and hope that it's got the right number of arguments. The way you call into Java from C++ is you use reflection. You have to look up types, you have to look up their methods and then invoke them. And in both directions, you have to hope you pass the right number of arguments or kaboom. I'm going to show you a few examples of what this code looks like if you write it by hand, and we did for many revs of our SDKs and getting into our apps. I think it's important to understand a little bit about how this stuff works, though hopefully by the time we get to the end, you'll see that you probably don't want to actually write any of this stuff yourself, or at least as little as possible. So let's say I want to expose a C++ into Java. I would write a little Java class that you can see here. The two important pieces are that first you have to load your C++ code somewhere. That's what this load library does. That static block will be executed the first time this class is loaded. And then you declare something with this native keyword that says, I'm not going to give you an implementation in Java. Instead, go try and find it in C++. So here's how you would implement that. And this is the simplest possible call that I can think of. This is a static method that takes an int, returns an int. So you'll see there's a whole lot of boilerplate at the top for how you declare this in a way that Java can find it. It has to be exported, has to be a C function, so that Java knows how to call it. It has this magic name that lets Java find it, tells it which Java method it corresponds to. There are ways to register that yourself with an explicit name if you really want to, but the magic names make things a little easier. Every Djinni function gets this Djinni env, which is the object that lets you talk to the Java VM. And in the case of a static method, you get a reference to the class of the static method. For an instance method, this would be a reference to the object instead. And then here's your actual argument, which is a jint. Jint meaning this is a Java-style int. If your ints are a different size in your C code, then you better deal with that. Same is true for the return value. And then once I'm actually in here, I'm just writing C++ code, and I can call my static method, and that's easy. Okay, let's move on to something a little bit more interesting. And as I go along here, I'm going to gray out code that is unchanged from last time. It looks like it's actually very faint, but you shouldn't have to read it at all, because the point is that's what hasn't changed. What has changed here is I'm calling a instance method in Java, which I want to call a member function in the C++, which means I somehow have to get a C++ object to call it on. the Java object won't do. A common way of accomplishing that is take a pointer to your C++ object, reinterpret cast it to a long, and stick it inside of the Java object. I know, you. So here's how I might do that. I actually have to call into Java, which means I start with the Java object, which is this, to make sure it doesn't collide with the keyword this. I say, okay, what's the method ID on that class? Get CVP, which is something I would write on the Java side. Here's its type signature. It's a function returning a long. J is for long. Then I can actually call it, call long method on this object with the method ID I got, and here's an argument. I shouldn't be passing that argument. That's a typo. It's a method that takes no arguments. But it turns out that it compiles and runs because it's just ignored, because this is a non-type safe interface. And then lastly, I take that long and I reinterpret cast it to my C++ type, and I can make my call. And all this hopefully works. And there'd be a corresponding piece of code that the Java constructor has to call to create the object, and the finalizer has to call to destroy the object. Yes?
So call long and call long type?
Yes. There's a separate call int method and call object method and all these things. That's how you specify the return type to Java and how it should interpret it. All right. Yeah, that's a standard that all the samples use. They use this and class. All right, so let's move on a little bit. What if I want to pass strings instead of ints? And again, the gray code is the same as last time, and here's what's new. This looks pretty simple. I can call getString UTF-chars. I get a C string out. I can pass that along. It'll get auto-cast to a standard string. And then I can do something in reverse. Notice that there's this release string UTF-chars. I hate seeing that in my code. That's manual resource management. I could wrap that in a unique pointer with a custom deleter, and I did. But for now, I'm going to show you all of the actual steps. So this is kind of annoying, but it's not that complicated. But it turns out this doesn't work. Anyone want to take a guess, or has anyone run into why this doesn't work? Yes, modified UTF-8. When Djinni talks about UTF, it doesn't mean UTF-8. It means modified UTF-8, which is the same for ASCII and most normal Unicode characters, but not for many of the obscure ones. Which means if you want to pass arbitrary Unicode through this, you're going to have to do something different. And we did, for instance, when we built the data store SDK, people want to put strings in their data stores. They want to be able to put any string in their data stores, not just a string that happens to match modified UTF-8. So this was not good enough. There's actually another bug. Anyone see it? More obscure. But this also, because it uses C strings, can't handle embedded nulls. If the string has an actual null character in it, we're going to truncate the string. So here's a version that deals with that. There are two ways you could do this. You could ask Java to convert it to UTF-8 for you and pass an array down here. What we do instead is we ask the string for its native representation, which is UTF-16, cast it, and then we use our own little converter. That's a little bit faster. We have a nice lightweight library, which is open source, by the way. Try it out. And then there's the corresponding conversion in the result direction. What have I skipped so far? I skipped errors. Sometimes things go wrong. In particular, almost everything I call on Djinni can fail, because everything in Java is allowed to throw an exception, an unchecked exception if it fails. Some Djinni calls will just crash if they fail, because it's something that you did wrong as a programmer, and that's what they decided to do. But anything that actually goes into the Java VM and does something may have to propagate an exception. The way that works, it doesn't use C++ exceptions, because this is really a C interface. Instead, there's a thread local state saying, I've got an exception pending, and it's your job as the programmer here to call exception check, see that there's an exception pending, and decide to return. And once you return to Java, it doesn't matter what you return. That's why I say arbitrary value there. Java sees, oh, there's an exception pending, and just throws that and doesn't return anything. But you do need to somehow short circuit your code so that it will actually return to Java. And then Java can fail. Turns out C++ can fail too if you happen to be using exceptions, which we do. So you're going to have to translate that in some way. Here's the simplest possible translation. Put this try catch my C++ exceptions, and I want to throw a runtime exception in Java, which is probably going to crash the program. but at least I get something through, and I can do that. I have to look up the class, runtime exception, and then throw one. It's all doable, but you might notice that the earlier code I wrote is now going off the top of the slide. This is quite a lot of code. So what's my point? This is tedious and error-prone, even when doing seemingly simple things, which is what I've been doing so far. I didn't show you how to pass an object with a bunch of fields. I didn't show you how to pass a list of such objects. And there are lots of details that you can get wrong. You can forget to check errors. You can forget to free your resources. You can pass the wrong number of arguments, as I apparently did in one of my slides. Of course, you can make this a lot simpler. C++ will help you. You can use RAII to do the freeing of resources automatically and make it more exception safe. You can capture a lot of things into helper functions and macros, which I did. I wrote the first version of our Android wrappers for the Sync SDK. So I came up with a lot of techniques to try and make this code more manageable. But no matter how much of that I did, I really came out of this saying, I never want to have to write this again. If only there was some magical entity who could make me never have to write this again. But it turns out there is. And the Djinni grants my wish. And instead, this is what I have to write these days. This says, I have an interface, which is implemented in C++. It has a method called demo that takes a string and returns a string. And then everything else I showed you is auto-generated for me. Pretty cool world to live in. And I'm going to show you a little bit more about how that works. But first, let me show you the corresponding side for Objective-C. And those of you who went to the Microsoft talk saw some of this. So I'm going to take this a little bit quickly and save room for some more exciting stuff. But I want to show something where this corresponds to the Java code. So the way we bridge Objective-C is using Objective-C++. This is a language that doesn't really exist as a standard. It's an unofficial overlay of two languages that the compiler authors have come up with. Think of it as if you take the diffs between C and Objective-C and then rebase that on top of C++, you get Objective-C++. It is, yeah. Clang does it great, Apple does it great. Which is why we use it. We were really afraid of it at first, but then experimented with it and it turned out to work. So we love it. There's you can get a lot of power because you can directly compose things. Objects can own each other across the boundary. And you can use your favorite techniques from either language, whichever one is most suited to your problem. Sounds great. But there are some disadvantages. It's pretty complex. You've got two types of exceptions to worry about. You've got two types of ref counting to worry about. Sometimes you create circular references. I had a great experience where automatic reference counting in Objective-C captured a strong reference inside of the lambda that I was passing to C++, thus creating a circular ownership relationship. There are very few tools that will tell you about that. And of course, you've got not two, but three kinds of bugs, because you've got all your favorite bugs from C++, all your favorite bugs from Objective-C, and a whole new class of bugs, which is when these two things interact with each other. So it's pretty hard to deal with, and you have to be a master of both languages to really debug this stuff. Net result of that is we use it because it's very useful, but we keep it to the boundary. We use it to build language bridge. We don't use it pervasively in our code base. Let me show you a little bit about what the language bridge looks like. Here's the interface that you would call in Objective-C. This is pure Objective-C code. There's no Objective-C++ here. And that means that your Objective-C developers building your UI can just call this as if it's a perfectly ordinary class. Here's the implementation of a method. This is Objective-C++ code, though it's a little bit hidden because everything's kind of magical. That underscore CPP object, that's a C++ object that's directly instantiated inside of my Objective-C object. Its constructor will be called automatically. Its destructor will be called automatically. Pretty cool. So it makes things very easy. So I've actually skipped ahead through several of my examples when I was doing Jni, because it's so easy to get this far. This is an instance method. I didn't have to start with a static method. So let's go through the same basic steps I did before. What if I want to pass strings? That's a little bit annoying, but it's still easier than it was in Jni. Do you think this has a bug? Who was paying attention last time? We don't have modified UTF-8 to deal with in this case. This is real UTF-8. What? It does, yes. There's no modified UTF-8 to deal with. This is real UTF-8. This still won't handle embedded null characters because I'm using C strings. So here's the version that passes an explicit length. It's a little bit more verbose, but if you've programmed Objective-C, you know it's supposed to be more verbose. Let's move on to error handling. So C++ code might throw an exception. So I'm going to want to catch that, translate it in some way. So here's the way I would translate it into an NS exception in Objective-C. However, NS exceptions are really only supposed to be used for things that are truly fatal. They're going to take down your program. So if you want a non-fatal error, you would use something like this and use an out param where you set an NS string, or sorry, an NS error. This is the normal way of doing things in Objective-C. I don't happen to like it because it's very C-like, but it's what you're used to.
Have you already been embedded null in an NS string? I've never seen it.
It does support it, and so does standard string, and so does Java string. And this, again, grew out of the data store SDK. We wanted our users to be able to put any string they want in there. So we wanted to take arbitrary data, including embedded nulls. It may not actually happen very often. So anyway, Objective-C++ allows code to overlap, so it's easier than Djinni. The memory model is more compatible, so you can get away with less marshalling if you want to. But it's still complex, and it's still a lot of wrapper functions to write, even though the wrapper functions are smaller. So I actually wish I didn't have to write that either, because building bridges is annoying once you've done it once. But fortunately, wishes comes in threes, so this wish can be granted too. And it turns out I can write that same interface, and it'll generate all the code I need for Java and Objective-C.
So you basically have this an IDL, essentially.
Yeah. So let me finally tell you what the hell I'm alluding to here. So we have a tool called Djinni, pronounced Djinni. That spelling is just an alternative transliteration. Those of you who've played Dungeons & Dragons might have seen it before. Djinni is a tool that generates bridge code between languages and currently supports Java to C++ or Objective-C to C++. So what does it do? As you mentioned, you put your interface in a custom IDL, which is pretty simple. Djinni generates the bridge code, does all the JNI marshalling, and gives you a Java proxy class that you can use from your Java code. Same thing in Objective-C. And your job in this case would be to implement an abstract base class in C++. Djinni provides the header file. You write the concrete implementation of that abstract base class. There's a slightly different but very similar set of things that you would write if you wanted to make calls in the other direction from C++ to Java or Objective-C. But it does work in both directions. What do we support in our IDL? There are interfaces, which you can think of like abstract base classes in C++. They can be implemented on either side. You can call in both directions, or they can be implemented on both sides. We have records. Think of these as structs. They contain pure data. They can contain primitive types or other records by value, not by reference. And lastly, we support enumeration, so you can define enum constants once and have them appear in all languages. That was a terrible annoyance before we had that. What are the types, basic primitive types you would expect? Notably, all of the integers are fixed width and signed, because that's what can be supported across all languages with no ambiguity. That doesn't mean we don't use size t inside of our C++ code when writing loops, but we don't let it go across the boundary. Supports floating point, strings, binary is represented as a vector of bytes. Also, you can pass around lists, sets, maps. These actually, list is maybe a bad name here because it maps to a vector in C++, not a list. But these are abstract names for the IDL. And lastly, it supports optional, which we use a lot for optional return values, things like that. Yeah. If I have time to look at the example, I can show you that. But it would be an array list in Java, an NS array in Objective-C, and the corresponding types for these other things. The maps we use and sets are actually hash-based, so it's unordered map. Other features of Djinni, it has static methods. These are particularly useful as factories to generate the concrete implementation of an interface. You can define constants, not just enums, but just any basic constant. It'll automatically generate comparators for your records, equals and less than, or implement comparable in Java or whatever the corresponding thing is. Or it can leave room for you to write your own comparators in your records if you really need to. One of my favorite features, the comments you put in your IDL will be propagated as documentation comments in all of the generated code. So if you're a Java developer, your IDE can show you the comments that tell you how to call this, and you'll see things that you would expect to see, just as if it was Java code. And most importantly, the code looks native on all sides of the boundary, and you can specify what you want your naming conventions to be even, so that it looks like your code, and nobody has to worry about the fact that this is ugly glue code. The idea is the ugly glue code stays in the middle, and what's on the boundaries is ordinary code. Let me give you a slightly larger example of an interface. So I could have an enum with 3 values here. I've got a record that contains that enum and also a string, and that deriving statement says that I want equality and ordering to be possible on this. It'll automatically generate. Here's an example of an interface that is implemented in Java or Objective-C rather than C++. You see the +J and +O rather than the +C I had earlier. I've got a constant, I've got some methods, and then I've got a static method that I use as a factory. All this should be pretty straightforward once you've seen it. We put the types as suffixes rather than prefixes. It's a little off-putting for C++ developers, but we think it's clearer. I hadn't thought of that. So why do we do it this way? Why not extract from the code like swig? Why not just do RPC and serialize everything? Because we are marshalling anyway. For the most part, most of the data gets copied. We like that it gives us a clearly defined interface. It looks native on all sides, as I said. We like that it gives you a very clear set of supported types for things like the lack of unsigned in Java, so you don't accidentally build something when you're going iOS first. Turns out it can't be used in Java. And it's explicitly language agnostic on all sides. So the fact that C++ is the backend right now is not necessarily true. We could replace that as well with other languages, or even use this rather than to generate a language backend to generate serialization code to Java or to protobufs, something like that, are all things that we've been thinking about. How are we doing for time? Okay, I have a slightly more detailed example. I'm going to scan through it really, really quickly and come back during Q&A or after this if anyone wants to see it more deeply. But I asked Tony, who works on Carousel, to give us something that's a little bit closer to what they would use. Obviously, still very simplified. There's a record, or a photo, which is a record containing an ID and a string for the file name. And here's an interface that lets you get the photos. The main thing I want to show you is how simple and native the code looks when you have to actually interact with it. So in C++, you're going to get a header file that contains a struct for that record. That's pretty basic. You're going to get a header file that defines the abstract base class for the interface. This is all you get in C++ because it's your job to implement the concrete implementation of this abstract base class. In Java, you're going to get this Java class representing the record. One interesting thing here is this annotation there. That's configurable. You can specify what you want the annotation to be. What we use that for is if you run ProGuard on your code to strip out unused code, it doesn't know what Djinni is doing, so it's going to try and strip out all these types if the only place that they're used is from Djinni. So you can write ProGuard rules that will use this annotation to know not to strip out this type. Here's the Java code for the interface. It's pretty basic, and in fact, I didn't even really have to show you all of this, because this is the only part that anyone interacts with. But this is the beginnings of the proxy class that allows C++ to provide the implementation. And I pulled out all the methods, but you can see that it contains that long ref that I mentioned in my examples earlier. On the Objective-C side, you get a header file containing a DB photo object for the record. You get a header file for a DB photo model object for the interface. And then you get a whole bunch of other code that you never want to look at, which is the actual glue pieces. I won't go into detail. So those of you who are keeping count might remember that I have one wish left. And traditionally, what you do if you're nice to your Djinni and you like them is your last wish is, I wish you were free. And I'm granting this for all of you today. Thank you. So Djinni is now open source. Please try it out. It's under an Apache 2.0 license, so you can do pretty much whatever you want with it. Includes a sample app, so you can see how things build across all these platforms we talk about. It's in beta. That doesn't mean we haven't tried it. We're actually shipping products with it right now. But that does mean we've only tried it for our use cases. So it's possible you maybe have some growing pains if you use it for something slightly different. But in that case, talk to Jacob here. He's the maintainer, and it'll be happy to fix your bugs, or send pull requests, and you can fix them yourself.
That could be very useful in enterprises using Java internally, actually, not just for mobile.
Absolutely, yeah. There's nothing here that is specific to mobile. It's just our target. And if you're using server-side Java and you want to easily write a library, go for it. So a few wrapping up conclusions. Multi-platform is a reality on mobile, also on desktop, and also when you want to do both, which we do. So think about it from the beginning. Building cross-platform as a way of doing multi-platform rather than building things multiple times has worked out pretty well for us so far. If you're going to do this, minimize duplication. Use it. We think it's best to build a native UI because you want things to look good, you want things to be fast, but you can share most of your actual logic, and C++ is a good way of doing that. C++ 11 and 14 are definitely up for the challenge. I think our application developers would have balked if they didn't have C++ 11, and we asked them to follow this procedure. It's a whole lot harder to do. We actually built the very first version of the Sync SDK using C, very quickly realized how painful that was and switched to C++. And hopefully we gave you a place to start, both in terms of tips and tricks and in terms of providing Djinni as something that you can try out. But we're far from done. Some of your questions already raised some of the things that we haven't done yet. We want to do more platforms. We're working on Windows, which is one of the harder ones because it's actually more different than iOS and Android are from each other, at least at the C++ level. We want to do bridge generation for more languages. We want to make more of the platform features available to C++ as we need them. Build more tooling. I'm going to be working on our build using GIP, as Alex alluded to, so I may have more to share about that later. And we want to eventually build out more and more application building blocks. As I said, Dropbox wants to build multiple apps at once, and we want to share between them, not just share between the same app on multiple platforms. And as Alex said, our main goal is to make cross-platform development as close to zero overhead as possible, that you pay just as much cost as it would take to build that app once, and now it's cross-platform.
So you use CLI for the bridging in .NET, or you don't use .NET?
Not sure yet. That depends on the needs of our apps. The first need actually on desktop is likely to be bridging to Python, because that's what our desktop client uses. But for desktop versions of Carousel and Mailbox, for instance, when they go to Windows, might want something slightly different. We're still figuring that out. Mailbox desktop is on Mac now. Let me know if you want to get into the beta, but it's not on Windows yet. So here's a bunch of links. You can find these slides if you missed anything or want to look more deeply into the sample code. You can find Djinni. You can find our other open source stuff. We'll probably be publishing a tech blog post about Djinni and this subject material, but next week after all of us get home and have time to write it. And here's our emails if you want to get in touch. So, thank you all for coming, and I'll take questions. Yeah, if you have questions, please come up to the mic just for the recording.
Did I hear you say you take a asynchronous network API and make it synchronous?
Yes, we do. Kind of a weird thing to do. Mostly because the Java one is synchronous, and that was simpler for the kind of code that we were going to write. So we just brought them down to a lowest common denominator.
Doesn't the Apple one use blocks too?
It does, you can use delegates instead, which would be easier to expose across. But yeah, basically, when a network call comes into Objective-C, I end up starting a run loop and just running it on that thread, getting all the callbacks, and then returning when I'm done. That was really tricky. We could have gone the other way and made it all asynchronous. We might someday, but for now, that works pretty well.
Okay, thank you.
Yeah, first of all, this is a great job. It's really hard to actually do cross-platform, and I think this makes it a lot easier. So thank you for that and making it open source. I have two questions, actually. The first one is, I see that you're exposing types on your interfaces, but I don't see anything about eventing. And if you're a UI developer, you actually care about events happening on your core, right? Do you guys support that type of interface too for events?
Yeah, one of the most common uses of an interface, particularly one that would be implemented in Java or Objective-C, is for listeners. So the UI is always the prime mover in our apps, but when it fires off various things in the libraries, often it will provide a listener for callbacks later, when new data is available or whatever, so that the interfaces in JNI will let you do that. You just pass I guess I didn't give an example of an interface being passed as an argument, but you can. And then it will be able to use a callback on a method of that interface.
And then my second question is, so when you are a UI developer, if you use iOS, you have notification changes when you're binding your objects in the UI and changes. I don't know if this applies to you guys, but in my world, we actually use, like in Windows, we have the binding mechanism. Do you guys have something to support that too? Or do I need to put a listener on every property when I want my UI to listen for changes?
I don't think I'm the right person to answer that, and unfortunately, all three of us here are the library guys, not the UI guys.
Okay. But your library doesn't actually expose those type of events.
No, we don't have anything in our libraries yet that is specific to building a particular UI with a particular framework. So those tend to be very platform specific. So that would be the job of the UI layer to do whatever is right for that UI framework, and then bind it as if necessary to calls down into the C++ code through an interface, or to have listeners for calling back out of C++ and then updating your UI.
All right, thank you.
Welcome.
So I noticed that you haven't avoided 90% of the C++ language features like some of the other speakers. So I was wondering if you guys gained some performance as well as cross-platform. I mean, was it just cross-platform that you gained by using C++, or was there also some speed improvements?
There was definitely performance gains. We aren't, since we're building applications, we aren't typically getting quite to the level of like instruction count sort of performance that affects power utilization, but we're not quite at the point where it's saving millions of dollars like it would be at Facebook or Google. But the performance benefits we have gotten is just that C++ lets you control your performance more than the higher level languages do. And did you make it to the talk earlier this week with Tony and Steven?
No.
Okay, you might check that out when the video comes out. Tony gave an example of how moving most of the memory usage out of Java and into C++ on Android keeps the garbage collector from getting in your way. And otherwise, the garbage collector would have made it entirely impossible for Carousel to have a smooth UI at 60 frames per second. Whereas by moving things into C++, managing our own memory, they can keep that fast and then shuffle data in and out of Java only as it needs it, reusing bitmap objects and a lot of other smart stuff. So check that out. I think that would be a good example.
So are you guys using like idiomatic C++, or do you have to like resort to like some acrobatic tricks to like do some memory saving or like some instructions?
No, things are pretty idiomatic. Unique pointers, shared pointers. We've embraced C++ 11. We like it. As I said on my here's our situation, we don't have a big legacy code base to deal with. We're building applications, we don't have to worry about SREs reading our code. So we don't have some of the same limitations that Microsoft or Google talked about in their talks. So we're trying to, based on that, be as aggressive as we can at embracing new features if they're useful. Obviously, we don't want to use new features when it's stupid to do so, and not be too clever for our own good, but we aren't holding back on things like exceptions or other things that other people may have shunned.
Thank you.
Yes, I was actually going to make that point. Thank you for reminding me that mostly our performance in the desktop apps comes down to networking and access to the database on disk. So a few extra instructions here and there don't usually kill us. Memory is a big exception, whereas where all that special stuff around garbage collecting came in. But most of the time, C++ is more than fast enough for what we have to do. And what we're optimizing is things like locks and database access and networking.
Did you happen to attend the talk on C++ hourglass-shaped designs?
I missed that one, no.
Okay.
Sorry.
Well, then never mind. I was just going to ask how your strategy compared to that gut reaction. I actually asked Alex earlier, but you haven't seen it.
I'm interested in watching that one. Yeah. There have been too many talks at this conference that I wanted to see, so I'm looking forward to the videos coming out. All right, I think we're past time, so let's call it a day, but you're welcome to come up and talk more.